Hello, Francesco.
Oh, hi. How are you?
Hey, good.
Hey, Zraven.
Hey,
It's wrong.
maybe for me, this is the last seminar in the odd times.
You're gonna switch with Alex,
Yeah.
No, but it's okay. I mean, 5 o'clock in Europe, it's 12 o'clock in China, so it's okay. I mean, it's not like 3 in the
Still
morning.
fine. Still, yeah, it's true. Well, it's 1 o'clock here, so in China it's better 1 hour back. Yeah, I think next seminar I will be there, switching to 5 o'clock.
Ah, you will be already in UK?
Yeah. Yeah, by 23rd I will be there.
But the next seminar is 23rd, so you
Yes.
okay, you will land and you will go immediately to the seminar.
Yes.
Good luck.
I will exactly land at 3 o'clock in UK time, so the 4 o'clock will be the seminar.
Very efficient guy, you see.
Okay, so you will be in the airport, passing passport control, believe me. It's a long story.
Okay. Okay.
Oh, hello, Francesca. Here is Irina. Hello.
Hello, Irina.
Hello. Hello. Ah, you already share your screen. Great.
Yes.
Great. But still, we have 5 minutes.
Yeah.
Well, I misread your title. Actually, I read it as Heart of Darkness. Darkness. No, it's Hearts of Darkness. It's plural.
Maybe you will start from some showing movie.
Movie?
Yeah, it's an old movie. Heart of
Old
Darkness.
movie, yes.
Yeah. Well, it's also a novel, right?
It's also
A novel.
yeah,
Yes,
also a novel,
yes.
I think. Yeah.
Hearts of Darkness is a novel. Okay.
Yes.
Yeah.
And the corresponding movie exists as well, yeah.
Okay, I didn't know about the movie actually. Okay.
I didn't know both.
If you type Hearts of Darkness in Google, you will see information about
Hearts of
this
Darkness,
movie.
a filmmaker's apocalypse. Is it a physicist's apocalypse? We'll be talking
No,
about.
I didn't know about the movie. I only know about the singular, about the novel by Conrad, right?
Okay.
Criticizing the colonialism. But yeah, it's nothing to do with that.
Are you gonna criticize someone?
No. That's not the colonialism for sure. Like it's not really related to the topic.
Okay, I'm gonna see. By the way, why do I see some text that the documents cannot be saved in iCloud? So I see little text.
A little box, yeah, there is.
Yeah, little box.
By the way, do you see the pointer?
No,
Yeah.
I see it, but there is a little box
Yeah.
appearing. I don't know. You can make it disappear, perhaps.
Here?
No, basically in the middle, just down.
Which explains us that you don't have space in iCloud
Yeah.
for some
I
reason.
don't see it.
Try to change slide. It's still there.
Yeah, it is still there. So
There is a box with written, this is not enough space
Maybe-
to save this document.
maybe open it from your laptop instead of putting the document in iCloud.
What does the box says?
It tells us that you have no space in iCloud and you have to pay some money. It's a paid
Okay.
seminar, you see.
It's still there?
Yeah.
Yeah, it is still there. It is appearing.
Only when you share the.
Yeah,
Then
once
you-
you start sharing, most likely it tries to save your slides. This is a problem. And maybe at this exact moment, you don't have enough space.
Okay. No, I don't
Yeah,
have
but-
space on the
Maybe
cloud. But now
generate the
it's still there.
PDF. Yeah, it's still there. Yeah.
You know, we still see it. It's not going away.
No, now
it
it is
PD
not here.
it
Now.
a
Now we don't
PDF?
see it. Maybe the PDF is better, Francesco.
Yeah,
No.
sure.
It's better you save the. PDF is better. Yeah. instead of this.
Okay.
No.
Okay, let me
Just
stop
convert
sharing,
it to
save the
PDF
PDF.
and maybe.
It's weird
instead
because
of-
sometimes I see that box, but now I don't have it.
Mm.
But okay, let's share the PDF.
Yeah, but I mean, nobody promised you that programs work as you expect them to work, so it's okay.
Okay. Now?
Yeah, perfect.
Yes, perfect.
Now everything is
Perfect,
great.
yes.
We can wait 2-3 minutes more, just in case.
Yes, we can wait a little bit. People will come in the last, in few minutes. And people will be there.
May I ask you that everyone who is not a speaker will mute themselves, please? Because otherwise I will have to mute everyone and nobody will be able to ask questions without my permission.
I see that most of people are mute.
No, there was some noise, so I don't know who is exactly, but no, I mean, because in case of noise, the only solution that I will mute everyone, then Francesco will unmute himself because he is a co-host, but everyone else will have to ask me before asking questions, which is not too much convenient.
No. Okay, maybe we can start. What do you think? 30 people is already.
Yeah, I think so.
Okay. Hello, everybody. Today, we have a pleasure to listen a talk by Francesco Di FIlippo. He will tell us about Hearts of Darkness, theory and phenomenology of non-singular black holes. Please, Francesco, 1 hour.
Okay, thank you very much for the introduction and especially for the invitation. It's great to be here, giving a talk here. Also, thank you to everyone for coming. So I'm going to talk about the theory and the phenomenology of singular black holes, and I'm going to start with a quick introduction, explain why should we care about this problem. So we all know, I'm sure we all agree, on the fact that we have a very successful and elegant theory to describe gravity, which is general relativity. And we live in a moment, in a period which is quite exciting for studying gravity, because we have lots and lots of data coming on from several collaborations, both in the gravitational wave spectrum and the electromagnetic wave spectrum. And so far, we have a lot of confirmation of general relativity. However, we also know that general relativity, it's a theory that predicts its own demise, its own breakdown. And this picture is taken from the famous paper, 1965 Perros, which proves that under reasonable initial condition, you will unavoidably form a singularity, or anyway, a geodesic incompleteness, geodesically incomplete spacetime. So we know that there are theorems starting from this 1965 paper that are telling us that, so the theory is telling us that we cannot trust the theory at some regime. And so we should expect that a full theory of gravity will somehow regularize the singularity and will allow us to describe it. And of course, there is some very simple way to handle the singularities, which can be summarized in the weak cosmic censorship conjectures. I stated here in a not necessarily super precise mathematical form two of the conjectures, which are telling us, the weak one is telling us that singularity are hidden from outside observer. So if a asymptotic observer do not fall into the black hole, they will never see the singularity because it's hidden behind an event horizon. And the stronger version, which is not mathematically stronger, but it's called the strong censorship conjecture, is telling us that GR is a deterministic theory. So we can give initial data of some initial time, and then we can evolve it. And we will not encounter Cauchy horizons or problems of the unitary evolution. And of course, and these are tempting solutions from the singularity problem that are telling us that we should not bother too much about it, and that we will not see any deviation if we are not following inside the black holes. So why do we care about what's going on in the singularity? I have two slides here to hopefully convince some people that would like to go for the easy answer of the cosmic censorship. And the first one is related to black hole evaporation. All the time that we discuss the information loss paradox, for instance, we see some Peros diagram like this one. And we see the black holes formed by gravitational collapse. We put some state on some initial upper surface. And after the collapse, we look at the state on another upper surface sigma 3. And we assume that the black hole evaporates completely and leaves a regular remnant, or in some cases, we can say that it leaves a singular remnant anyway. So you can see the difference between these two diagrams is that here r equals 0 is a regular point, and here instead we assume a naked singularity. But anyway, regardless of which one of the two possibilities we have, we still have the singularities in the past of some observer in the region that is acceptable classical region because the space-time here is approximately flat. And so if you want to understand in this formulation of the paradox, so which we compare the state of sigma 1, the state of sigma 3, which you want to understand what's going on with the information loss paradox, in my opinion, we should also look at what's going on with the singularity, because the singularity can actually influence part of the space-time. And in fact, in semi-classical gravity, if we ignore the singularity, or we can study this diagram here, in which we have some part of the space-time missing. So the fact that if we, for instance, put a pure state on sigma 1, we do not see a pure state of sigma 3, is no longer a problem because we have a part of space-time missing. So in my opinion, feel free to contradict me and to stop me and say that you disagree. If you want to understand what's going on with the information, we should see what's going on with the singularity because it can influence the space-time. So this is the first motivation. A second motivation is something that it's more from a phenomenological perspective. I want to argue that we should keep an open mind. And this is kind of a lesson that maybe we can draw from Newtonian gravity. So let's do a mental exercise. And let's imagine that we live in a region of the universe, of space-time, in which we cannot experience strong gravity effect. We cannot experience high energy particle. We cannot directly probe them. And so in this portion of the universe, Newtonian gravity is an excellent description of space-time, of the theory of gravity. And the question is, should we then accept the impossibility of proving general relativity? So in general, proving physics beyond Newton? We know the answer, and we know that the answer is no. And one of the reasons are gravitational waves. So gravitational waves are an effect that is something which is completely, does not exist in Newtonian gravity. It's something that is generated in region where Newtonian gravity breaks down. So when you have collision of black holes. However, they do propagate and they do travel on a region of space-time in which we would have expected Newtonian gravity to be an excellent approximation. So even if the space-time is approximately flat, we can probe the modification to the Newtonian gravity due to the full theory of gravity, which is in this case is the general relativity. And this is just to say that a priori, we should keep an open mind that the same might happen with general relativity and the new theory of gravity. So it's true that outside black hole, we a priori do not have any reason to expect breakdown of GR, but we do have reason to expect breakdown of GR inside black holes. And if we do not study this possibility, we will never be able to understand if this modification will propagate also outside. So at least from a physicist perspective, where the end word is always given by the experiment, we should study this possibility and we should study the implication, and then we should see if it is possible to prove it experimentally or not. So with this in mind, I will quickly explain what is the outline of this talk. So as I said, I want to study possibility of singularity regularization. So the first step will be to start to categorize non-singular black holes and to see what are the space-time candidates. They can mimic the property of a black hole, but they do not have any singularity. And we will then focus on some of these classes. And some of these classes, as you can expect, in principle do not have any phenomenological feature outside the horizon. And so the best you can do is to study if these are to study self-consistency issue, to study if you have some theoretical reasons to study theoretically what are these objects, and to see if there are some self-consistency issue that you need to address, or if these are perfectly fine space-time. And then again, we should study whenever we can. We should look for phenomenological signatures. So I will give just a few examples of each of these possibilities. And let's start with the first step, which is mainly based on this paper here, which now is not. I mean, it's already has a few years now, but I still like to start the talks on this paper because I think it set the stage very well from the following discussion. So I will be quick because I talked about this several times at the moment. So, but still, I like to mention it at the beginning of the talk. And so the goal of this section is to provide a classification of space-time that are not singular. And the way we are going to do this, so this task, so what does it mean to provide a classification of non-singular spacetime? The way we are going to do this is to provide a classification of the way in which spacetime can avoid the Penrose singularity or incompleteness theorem that I mentioned before. So these are the assumptions of the Penrose theorem. The main one, which we will still assume, and then maybe some people could criticize, and I can agree, is that we can describe gravity using the standard tools of pseudo-Riemannian geometry. So smooth manifold provide an adequate description of spacetime. Of course, it's possible that this is not going to be the case, that once we are in quantum gravity regime, we will not be able to use smooth manifold, and we should go to a discrete description. This is definitely a possibility, but this is a working assumption. Once we assume that, the theorem also assumes global hyperbolicity, so which is necessary to a well-defined unitary evolution. And also it's assumed null energy condition, so which is null convergence condition, sorry, which are equivalent to the null energy condition and the Eisenfeld equation. Once you assume, once you have done this assumption, you can prove that the spacetime is geodesically incomplete. And the way you prove it is schematically be divided into parts. So in the first part, you prove that if you have a trapped surface, which is this one dimension is suppressed, so this circle is a two surface. At each point of this trapped surface, you know that we have two null direction. And the first part of the theorem uses the null energy condition to show that all the geodesic will focus in one point. Of course, it's not really focusing in one point if you're outside spherical symmetry, but for just to draw to have a nice drawing, I put a spherically symmetric situation, so everything just focuses in one point. Otherwise, we would say that all geodesics have a turning point. And then you can geometrically prove that the presence of this focusing or turning point for all geodesics is actually impossible. It's incompatible with global hyperbolicity and the topology of spacetime. So now the classification of spacetime that are not singular is now it's a much simpler task of classifying the way you can avoid the existence of this focusing point. And so these are the assumptions that we are going to make. So there are the same assumptions of the Sperrio's theorem. However, we are not going to assume the null convergence condition. So we have to break them somehow. And we are assuming that the space-time is complete and the absence of curvature singularity.
Can I ask a question?
Of course, yeah.
Yeah. Well, I'm just wondering about because you want to avoid singularity classically, right? You want to find space-time to not to have any classical singularity. I'm just wondering if we have consistent theory of quantum gravity, especially we need it to understand the space-time singularities.
Yes.
Then we don't really need to think about classically, right? I mean, if we have consistent quantum gravity, singularity is automatically avoided by its nature.
No, absolutely. This is what I was saying. The fact the main assumption is the first one, which is a working assumption. The point is that we are trying to make something which is as model independent as possible. So you need the fewest assumption that you can make, and this is one. And the assumption is that you can provide some effective geometry. This is true for many models. Like you have some toy models inspired by quantum gravity theory. You have a modified gravity. It will hold true for any modified gravity theory, but it's not something that is always going to be true. So this is something to keep in mind. However, this description does include many results that are in the literature. So this is the power of this description. But as you mentioned very correctly, we should keep in mind the limitation of the model. The limitation of the model is that if you lose this effective description, you cannot use the model anymore. So this is an effective description that can make sense, or it might not make sense, it might break down, and we should just keep this in mind. We should just explore any possibility. Right? It's a working assumption. Thanks for the question that allow me to do this classification. And I will not go through the details of the classification. I will just quickly discuss the possible classes that you can have. And there are not that many possibilities. The first one is something that we can call evanescent horizon, in which you have some situation of like this. So you have a gravitational collapse that forming a black hole. In general relativity, you form an outer and inner horizon. So if you have matter collapsing, you form outer and inner horizon and a trapped region. Then the inner horizon goes to r equals 0. I mean, actually have the Pareto diagram of general relativity. You have you form the outer and inner horizon. The inner horizon goes to r equals 0, and then once you arrive to r equals 0, you form a singularity. So to avoid the singularity, the inner horizon cannot reach all the way to r equals 0. And the first possibility is that outer and inner actually merge in a finite time that can be huge time or short time, depending on the model. Here I have, so just to explain the diagram, this shaded region is the trapped region. These blue lines are lines of constant radius that you can see that these are time-like or outside the trapped region. and space like inside the trap region. So server inside the trap region are forced to go, if they move in a time-like or null way, are forced to go in the direction of decreasing radius. So this is the definition of trap region. And this, I mean, a priori, the geometric classification cannot give you any hints on what is the physical mechanism leading to this. It can be something related to Hawking radiation, which will take a very long time, or it can be something that like bounds, like here in this diagram, in which you have a black hole-like configuration, and then you have some switch off of gravity for some reason. This happens in many models. And this leads to a white hole-like configuration. So here you have an anti-trapped region. So there are many possibilities. The common feature of the diagram in this class is that you have both an outer and inner horizon. The second class is a class of spacetime that does not have an inner horizon, but you have something like a minimum radius. So it's something that resembles a wormhole-like geometry. So if you look at this diagram in the left, you have a trapped region, this again shaded region, and then you have a minimum radius hypersurface. So it's similar to a wormhole throat. This throat is, because it's inside the trap region, is hidden from outside observer, and it can only be traversed in one way. So this is why we call it one-way hidden wormhole. And you can actually have something which is, instead of a global minimum, which is a local minimum, like here on the right. I will not focus much on this possibility. We should, but it's something that can happen. There are some problems relating how to form this spacetime, especially the one with the global minimum, because you need some topology change. If you assume that in the far past you have something which is close to Minkowski spacetime, here you have a minimum for the radius. So at some point you need a change of topology, which cannot happen if you have global hyperbolicity, because all the Cauchy slices has to be isomorphic to each other. So you cannot have a topology change. So the formation of this object is non-trivial, but maybe it can happen in full quantum gravity regime or these kind of things. So these are the second class that is possible. And then you have a third and fourth class in which you push either the wormhole throat or the place in which the inner outer horizon merge at infinite affine distance. But they are quite similar to the first two qualitatively. So basically, we can classify the possible spacetime into few classes. And of course, the starting point was the presence of the trapped surface. So we should add an extra class, which is the objects that do not have a trapped surface, which are maybe very close to forming a trapped surface, but they do not have it. So ultra compact objects that are similar to stars, but the surface is very, very close to the bulb horizon. And now in the next part of the talk, I will actually focus on regular black holes. So the first class, in which have both an inner and outer horizon. I will explain a bit better the geometry, and then we will look into the phenomenon that goes by the way of mass inflation, and look at the limitation of this of the analysis and what does it mean, this effect. But before that, I think this is a good place to stop if there are other questions about the classification before going to the second part of the talk. So is there any question here? Well, I will continue.
I have a short question related to the wormhole thing. Is it similar to what we know in the case of Schwarzschild geometry? I mean, what kind of wormhole you're talking about? It's not clear. Can you elaborate a bit?
So this is, yeah. So at this stage, I'm not giving any geometry. I'm just any specific geometry. I'm just giving some feature that geometry of each class might have. And in each class, you can have different type of geometries, but they will share some common characteristic. that allow us to study them somehow. The one in this class, what I'm saying is that you have some, so these dotted lines are lines of coastal radius. Again, they have time like outside the trap region, in space like here. And you have a minimum value for the radius. So this is similar to, so this is a wormhole-like geometry. But so you do not have any R equals 0 hypersurface, for instance. But you have a minimum value. And this is inside the trap region, this one. So yeah, it's similar to an eternal Schwarzschild spacetime, if this is what you were asking. It's similar to that. But yeah, you do not have a singularity at R equals 0. You have you go to another section of the spacetime at R equal R minimum. So yeah, I mean, qualitatively speaking, if you cut these regions here and here, this looks like a Schwarzschild spacetime. But this is not a singularity. This is something that you have some bounds. So the radius decreases in this direction and then start increasing after the throat. So you can write some geometry. I don't have it here, but yeah. So
except that there is no singularity, the wormhole is similar to Schwarzschild that is connecting these two regions.
Yes, to eternal
on the right and left, right?
Yeah.
Okay.
Yeah. So the wormhole throat is this one. I mean, of course, you have something similar to that, like commenting here, but the wormhole throat is this one. But the crucial point is that this is similar to the eternal Schwarzschild spacetime. It's not similar to a black hole that's formed by a gravitational collapse, because you need to have some minimum radius. Okay, thanks for the question.
Excuse me, may I ask a question?
Yeah, sure.
You assume spherical symmetry or not at this moment?
Yeah. So yes, I forgot to specify this. So most of the steps that do not require spherical symmetry, because most of the steps, but because the tools that we use are the ones of the Ferro's theorem, so you do not need it. However, there are a few places in the analysis, I didn't go into the details, in which we do use it. So if you go beyond spherical symmetry, you might have more possibilities. It's not clear if those are actually viable. So we use spherical symmetry to rule out a few possibilities, a few classes. So you might have more if you go beyond spherical symmetry. And of course, beyond spherical symmetry, you can have a bigger combination of classes. So these are some classes. The generic spacetime will be a combination of them. And if you go beyond spherical symmetry, you can have more combination. But yeah, there are some steps in which you need spherical symmetry, yes. Even though the main idea does not require it.
My question is that there are two questions here. If you consider, for example, Kerr spacetime and make regular this inter ring of singularity, make it smooth, you have spacetime structure diagram which will be quite different from what you have shown.
Yes.
It will be infinite number of sets, so it will be other complete possibility. And if you lose spherical symmetry, the question when you represent solution using Penrose diagrams, you can have different sections. So, and in different sections maybe different behavior. So somehow where it's hidden here.
Yeah. So the first point about Kerr. So I agree on both points. Let me just give a couple of comments. So we also assume global hyperbolicity. So so if we consider some Kerr-like structure, we should stop at the Cauchy horizon. So we will not continue beyond the Cauchy horizon. And then this is what the second point is exactly what I was meaning when I said that the generic spacetime is given by a combination of the spacetime in this of these classes, which in spherical symmetry means that you can have something like this, and then you put some bounds-like structure, and then you have a recollapse, and then you may end up in another classes. So these are kind of trivial combination. Beyond spherical symmetry, instead, you can have that at each value of theta, you have some different behavior of the the null race. So you will have something like some section may look like this and some other section may look like this, because, yeah, of course, a Penrose diagram provides a clear picture of the spacetime only when you have spherical symmetry. That's why you need to fix the angles. Yes, there is I definitely agree with these points. Yes, thank you.
Sorry, there is one more question. Yes, Roger, please ask your questions. I see you with your
Okay, thank you. Yes, I have a question about this classification. Does it change anything if you have in gravitational setup additional symmetry, like, for example, supersymmetry or conformal symmetry? Do you think that just the analysis that you show is gonna change in any way? And later I could have some further question. Yeah, please.
Yeah. So if so here we're only assuming that you have an effective geometric description, and if you put more structure, then maybe it will be like theory dependent, but you may argue that some of these classes will not be realized. I mean, it's possible, but you will not have more possibilities, let's say, because this is the minimal number of assumptions giving some classes, and then you can put more. For instance, we have another paper more recent in which we consider we added the possibility of Lorentz violating theory, so you can have something like a universal horizon and this kind of objects. And from the beginning, we knew that you cannot get extra classes. In principle, you can have less if you have more structure. I do not expect this to happen, but of course, if you add more information, you can study better the classes. You know, like you can say more things. But this is the very minimal description. Right?
Do you mean that adding more structure can only cannot add anything new to this classification? Yeah,
it could. I mean, you could be able to add a more refined description. You could be able to constrain the geometries more, but you cannot create a new class because this is we were just. I mean, of course. Within the same class, you can have a space-time that looks quite different from each other. So it's not like this is a perfect classification. The point of this classification is that we try to identify some common properties of the solution. So if you go in the literature and see many models that solve the singularity, you can see that they share some properties, all of them. And this is not an accident. This is because the geometry is not, you don't have that much freedom. And of course, in spherical symmetry, you have much less freedom than this. And most of the models are so spherically symmetric space-time. So this is also one of the reasons why. But yeah, it can be interesting to add more structure and to see what are the constraints. But at the moment now, I don't know your specific example, what will lead to. But yeah, it could lead to a more refined description, let's say.
Okay, and then some kind of follow-up question. Do I understand correctly that for your classification, when you have this way how to avoid Penrose, you do not use Einstein equations? Yeah, so
no. Yeah.
So this is, I mean, you try and you attempt, I think, successfully to find something that is independent on a particular gravitational field. So, so the assumptions are based on a geometry, but you do not use, because before in this condition, I think with the positivity, yes, that you used with Ricciardo equations, you could use the Einstein equations, but here I don't see it. So I guess it's independent.
Exactly. So, so basically, just this cartoon here, like if you use Einstein equation in null energy condition, you form this focusing point. You should do something that does not form it. And okay, this is something very simple to classify. You just look at the outgoing and ingoing null rays. You study the expansion parameter. So you see how they behave. And this is the basis of the classification that we have. So absolutely no, like you actually we know that you need to violate the null convergence condition, because otherwise, yeah, you will have a theory.
Okay, thank you very much.
Okay, thank you.
I have a short question, if I can ask.
Yeah.
So,
Yeah.
Since you have mentioned the second class with wormhole, I'm curious, observationally, how to distinguish these two.
No, okay. So if you have something like this,
Yeah,
which outside
you mentioned,
can be exactly equal to Schwarzschild or Kerr if you have the rotating one, or the modification will be very, very small, very suppressed. Probably observationally, it's going to be extremely difficult, if not impossible, to distinguish this class. This one, it's probably it can mimic very well because you can easily write something which at least is vertically symmetry. It's very easy to write something that is that in the interior you have this kind of structure and the exterior is exactly Schwarzschild. You use some bump function and you modify the, so you put the area radius, you just put the Schwarzschild geometry, and the other radius, instead of being r squared, you put something which has a minimum, but then far from the minimum it goes to r squared, right? So this, in principle, you can put constraints, but there will always be classes that elude phenomenology from here. And this has to be expected, right? It's to be expected that there are possibility of classes that do not lead to any phenomenology.
okay. So it's very much not possible to detect.
Of course, the problem with this object, as I was saying, of course, the problem with this solution is what I was saying before: the fact that you need a topology change, which we do not know how to do. That's the problem with this geometry. So as I said, for the classes that do not give any observation, you can study the self-consistency issue, and in this case, it will be topology change. I will not discuss much more because I don't have much more to say.
Okay.
But for this other class, I will say a bit more. This non-singular black hole geometry. Okay, this is okay. There was some transition. Then before, we had to go to PDF, and on the transition, I bought the same slides. So sorry, this might happen again later. Because there was some problem in the screen sharing, so I need to go to the PDF. But okay, it's minor. So this is the type of geometry we will focus on the second part of the talk. And for simplicity, we focus on the static spacetime, which is technically speaking outside the classification that we had because it's not global hyperbolic, but this is just an artifact of the static approximation. And then the result can be easily translated to a time-dependent scenario if you have a separation of scale. So this is just for simplicity of the discussion. We consider a static geometry. So if you look at this geometry, you can look at the condition for the horizon. Where are the horizon located? And the horizon are located where this function f is equal to 0. And you can easily check that this implies that you have an even number of horizons, simply because asymptotically you need to recover Schwarzschild. And in the interior, spherical symmetry. To avoid the curvature singularity, you need to go to fs to go to 1. So you have an even number of horizons, which is, in this case, for this function, it will be 0. This will be 2, and this will be a double horizon. You have the general solution. And one one quantity gravity necessarily negative at the inner horizon. These are just some example of geometries, that are introduced in the literature. I should have added some references. I sorry I didn't, but so this can be introduced as like you introduce a geometry with required characteristic, or there are some toy model guided by quantum gravity that regularize the singularity, and they often give some geometry of this type. But okay, it's not particularly relevant for the rest of the discussion. And this causal structure is exactly the same as the one in Rese Nostrum, except for the fact that R equals 0 is now regular, but instead of being singular. And in Rese Nostrum, we know that the inner horizon is generically unstable. And this is actually good because of the interplay with the strong cosmic censorship that I mentioned before. So in radius nostrum, the singularity is time-like, but if you add a small perturbation, the instability of the inner horizon is such that okay, there are still some open discussion, but it's such that the singularity becomes either null or space-like. And this helps with the strong cosmic censorship, because otherwise the inner horizon would be a Cauchy horizon. So the observer could go, if your observer could go beyond the inner horizon, then you will violate you will not be able to describe in a deterministic way, starting from the data that you give outside the black hole, because you will need to give initial data of the singularity. So this is actually a welcome feature, because you have a singularity anyway. But let's see what does it mean in the context of regular black hole, if you can do something similar. And of course, if I say you want to do something similar, this is quite tricky, because we do not have the field equation. So this the result will definitely be less stringent than the one that we have in general relativity. So this means that if you want to do this, we need to consider, first of all, a geometric approach, so not a dynamical one, and we will have to make a few assumptions. And in the rest of this section of the talk, I will not care that much about the technical steps. I just want to, so they will be on the slides, but I put them on the slide just because I want to stress what are the assumptions and what are the limitations of this approach, because I feel that sometimes these are kind of overlooked. So it's kind of strange to present the result of your work focusing mainly on the limitations, but I feel like for clarity, this is quite important. So there are limitations, I want to stress them, but also there are strong points, and I will stress them as well. And okay, so the background geometry per se is of course is completely fine. We can write it. It has a simple form. We want to study if so what is the interplay with once you add perturbation on the geometry, and we start adding a very simple form of perturbation, which is given initially just by two null shells. So we add two null shells in the space-time. These are that we can. So these are 3 and 4, two null shells that meet in a point with the two surfaces with the radius R0, and give rise to other two null shells. So we have two questions actually. Is this a reasonable type of perturbation? And two, what is the back reaction of this perturbation of the spacetime? Is this a reasonable perturbation? The answer is yes. First of all, the black holes are not in vacuum; they accrete matter. And then we have approximating this to be null shells, and this is a good approximation close to the inner horizon because of the blue shift that is experienced there. So if you throw some particle from outside, then this will be collimated, getting closer and closer to the inner horizon. So you can approximate them as null shells. And now, so if you are interested in the region close to the inner horizon, this is a reasonable approximation. And now we use purely geometrical arguments to relate the geometry in the different regions. And you get this result, which is okay. It is what it is. But what I want to stress is that the Meissner-Sharp mass MA in one of the regions of the spacetime, this one A, which is the one in between the two null shells, is given by this equation here, in which M in and M out are the jumps of the Meissner-Sharp mass across the shells.
Excuse me, when you speak about closeness to the inner horizon, there are two branches, left and right. So yeah. Where are you trying to go, to the right or to the left?
So usually we do it on the right, but you can actually, because we will care about, so we drop it like in this way. So this is the type of perturbation that we're adding. So we have something which is accreting. We are from here, and we go for large value of advanced time. So v goes to infinity. So we are getting close to the inner horizon to the right. This in this show, we have some null shell coming from this other asymptotic region, but we should imagine this coming again from the same asymptotic region when you have a gravitational collapse that just backreacted by the geometry, so you have a star collapsing and it's emitting these ones. So yeah, we go here.
But in case of a regular black hole with a Euclidean core, there is a danger about the left-hand side as well, because rays coming to the center and go close to the to the left horizon, and it's the origin of infinite blue shift of the quantum radiation from regular black holes.
Mm-hmm. Yeah,
So
no, you like okay. Here I have the discussion close here, but I don't see much difference during the discussion also here, because as you said, if it is like if you go from this type of diagram, the right part will be this section here, and the left part will be this one, and yeah, they are quite similar. Like we can do the same. And what I want to stress here, except for the specific form, is that this quantity here are the jump denominator sharp mass across the shells. And we are assuming that these are non-zero. And this is, I want to stress, this is an assumption. And we assume that these are proportional to the energy of the shell. So why this is an assumption? If you consider something like a tabletop experiment to mimic black holes, so for instance, analog gravity, you can mimic the space-time, you can mimic the geometry, but you do not have anything related to any field equation. So actually the perturbation are not felt from the background geometry. So basically this jump will be zero and you will not have any perturbation. Right? If you have something, given Fro was asking a question, if you have something like limited curvature gravity, I guess in that case, this difference, once you are close to the limit curvature, this difference will go to zero because you cannot increase the curvature more. So this is the assumption of the model, that the energy of the perturbation backreact, even just a little bit, but in a way that is proportional to the energy of the shell, which is something that is, I think, quite reasonable. But you need to keep in mind where is the assumption, and I think this is the only assumption of the model. And now, so basically, this that we are saying that this is amount is it's changing, it's proportional to the energy. One thing that you can say is that it is proportional. So the energy of the shell will change the asymptotic mass. So you can actually compute the jump in the Misner-Sharp mass. And okay, now if you put these things together, you get something that in the region A is divergent when you go closer and closer to the horizon, because to the inner horizon V is equal to infinity, and so you get an exponential divergence. So what you can say is that a small perturbation is a huge backreaction of the geometry. Now, this is divergent, but notice I didn't say that a small perturbation creates a curvature singularity, even though this is divergent, because I think this point is kind of misinterpreted sometimes. So it's misinterpreted the limitation of the result, because we have a background geometry. We assume that the perturbation do not change the functional form of the geometry. And then we continue the model and we get something which is divergent. But of course, once the perturbation, the backreaction is huge, this linear approximation somehow is going to be violated. So you cannot use this result without using the field equation. You can never prove the fact that you're going to create a curvature singularity. All you can say is that you have a large backreaction. So all the models that give you regular black hole geometry does not mean that in these models you have once you perturb the geometry, you create a curvature singularity. It's impossible to prove that without the field equation. But these models, maybe they are not complete, because you should include the backreaction. The backreaction will be large. So what we are saying is not that these models are somehow wrong. We're never saying that, but they are incomplete. You should study what is the interplay with matter. And
sorry,
you could, yeah.
How do I see the large back reaction?
So we are just assuming that in the four regions spacetime you have the same functional form, right? And then you can show that the business sharp mass and hence the curvature invariants are divergent if you do this assumption. But at some point, this assumption will break down because at some point the back reaction is too large that you cannot consider it as a small perturbation of the geometry. So once the back reaction is order 1, so this the variation of the business sharp is large, then you will need to plug the field equation of the theory and do the full nonlinear computation. So what we are saying is that this background geometry are perfectly fine, but once you add the perturbation, this back reaction is large, and you need to study the field equation of the theory. Now you can do the model. You can be a little bit more refined. It's, instead of 2 null shells, you have 1 shell and 1 continuous flux of energy. This, I mean, I will skip it because there were several questions, so I'm quite late. Just want to say that qualitatively, you get something that is very similar. You have some more freedom. And what I want to stress is that for some geometries, you get something which you get, again, some exponential blowing up of the business sharp mass and then of the curvature invariance. But at very late time, this blowing up became polynomial. And however, this should not be interpreted of saying that these geometry are less unstable, because you can see here the initial mass is order 10, and the blowing up becomes polynomial when the mass is order 10 to the 23. So the back reaction is extremely huge. So the model will break down somewhere here. So you cannot trust the model at this point. This is way beyond the regime of validity of the model. And the fact that you have initial exponential, this is completely generic. So we should keep in mind that this model is limited, and then we can prove that a small perturbation is a huge back reaction, and that's it. This is what we can prove. We cannot say, but here it's this for Bardeen it's exponential, and for Hayward it's polynomial. This is different. No, this is exactly the same because the model breaks down here anyway. So can we make, so now I will just, okay, we skip the phenomenological part. Anyway, Luke asked me to talk about mass inflation, so it's okay to skip the phenomenological section. I'm also happy that there were many questions, so it's okay to skip the last part of this talk. So I will finish just saying that can we make this regular solution stable? And if you look, there are some recent papers that they argue that you can do that just considering the effect of Hawking radiation. I would just want to mention quickly that I personally disagree with this statement. So how the statement goes? So the statement goes that Hawking radiation at a very late stage will be the dominant effect, because at very late stage the classical perturbation will be washed out, and the Hawking radiation will be the dominant one. And basically, you have, given that this decreases the mass, you have a different sign for so the null shell will have a negative energy here. So the mass is decreasing, it's not accreting as for the classical perturbation. And you can show that the business sharp mass, instead of going exponentially, it goes linearly, and it's actually negative. So it's much lower divergency, but okay, first of all, it's still divergent. And second, as we were saying before, Hawking radiation will be dominant after time m cube. And so this is well beyond the regime of validity of the theory. So I think that this is pushing the model well beyond its regime of validity.
Excuse me, when you speak about Hawking radiation, it's radiation at the infinity. And now you're speaking about mass in the interior. So
yeah, I agree.
Because interior you have a combination of different stress tension tensor will contain polarization effect. So it's too naive to think that mass in interior is the same as mass visible in exterior based on the Hawking calculation. So it's a little bit.
Yeah. No, I mean, okay. So, okay. I mean, this is not our paper. I agree with you. I mean, just say that even in the very idealized computation, this does not help because, like, it's true that technically speaking, the divergence is only at v equal infinity, where we are at the inner horizon. So for the exterior, this is v equal infinity, but the model breaks down well before, so it breaks down somewhere here. So even in the idealized computation, in which you just have this, you just say that the mass is changing given by the energy at like in the way consistent with energy at infinity in the easiest possible way. So basically, you model Hawking radiation with a simple way. Even in this case, does not really help because it's true that the divergence is slowed down, but it will start to slow down at some point, you know, very, very in the future. That very, very close to the inner horizon where the model already broke down. So that's all what I wanted to say. So the model, I think we should. I mean, it will break down at some point where Hawking radiation is still negligible, and so we can avoid all these complications. And the last point I want to say how we can have, if you can have something which is stable, is that the stability goes by, it's regulated by the value of the surface gravity at the inner horizon. So one possible question will be, can we build something which is at the inner horizon, the surface gravity is 0, while at the outer horizon, you recover something similar to a black hole? And the answer is yes. You can easily write a metric, and then we've done it. We've written a metric that ticks all the boxes. And then we check that there is no instability. A small perturbation causes a small effect. These are perfectly fine in both models, the two null shells and this ORI model with one null shell and one flux of energy. However, this might look an overtuned solution, right? Because, I mean, you are really tuning the geometry to have 0 surface gravity here. And I don't have much to say. It's nice to say that there exists objects in this geometry that are stable, but whether or not you are going to form them, it's a much more difficult question. Maybe you can form them as a back reaction. As I said, once you have one geometry like this, you have a large back reaction. Maybe this back reaction is going to tune to 0 the value of the surface gravity. It's possible because this is the only stable class in this, the only stable geometry in this class. But yeah, I don't know. It's a much more difficult question. I will not enter now. Maybe something that will be addressed in future studies. And yeah, the last part of the talk would have been to look for phenomenological signatures. I will skip it. I just want to say something like, I want to just quickly say the result of one possible cross-strain that can come from phenomenology, which is a constraint of objects that are not black holes, but they have a surface, or they're ultra-compact objects. They have a surface which is at least partially reflective, and the fact that so they are similar to stars, but very, very compact. And the fact that black holes are not in vacuum implies that there is a flux of energy going from the accretion disk to the object. And if the object is not a black hole, but it has a partially reflective surface, you will have a flux of energy going from the object to infinity because you will reach thermal equilibrium. And this was initially claimed that this rule out every type of ultracompact object. But there are two effects that that are important. The first one is that if the object is very compact, you have strong gravitational lensing. And the second one is the role of absorption that we mentioned here. So first of all, if you have an object that is very compact, most of the energy that is radiated by the object falls back into the object itself. So this was studied here in this paper. So it's true that you will have some part of energy going to infinity, but only if it is emitted almost perpendicularly. And this gives you a time delay for the formation of this outgoing flux. And if you study the problem, you see that this time delay is very large. for a very compact configuration. And this allow you to cast a constraint which is very stringent. So this is the compactness parameter, is very stringent, but it's not without everything. So objects like fastball are still allowed by this constraint. The problem is that here we're assuming that the surface is perfectly reflective. What happens if you add some coefficient of absorption? So for a black hole, all the energy is absorbed. We want to add something that maybe a fraction of energy is absorbed, but the rest is emitted. And I just want to show you how this constraint is modified. This constraint is modified very, very strongly. So this is what we show in our paper, is that even absorption as small as 10 to the minus 8 weakens the constraints by 7 order of magnitude. So a small absorption weakens the constraint in a very strongly. And also, if you have an absorption which is order 1, you really don't have a constraint that you can cast. So I was a bit fast of this, but I just wanted to give the message that from an observation point of view, we do have a lot of data coming out now, but these objects are quite tricky to test, and we should also keep it account that there are effects that are not so easy, and even a very small absorption coefficient could make this object almost invisible. Even if like for a black hole, the absorption coefficient is 1. Even a very small absorption coefficient is spoiling the constraints strongly. So
I see a question from Alexei Koshelyev.
I just actually finished here, so I will leave.
I can wait till the end of the talk. No, don't worry.
Okay, great.
I can leave the slides of the final remark. So just we have classified the non-singular black holes in a few classes. We have seen, then we have studied more in details conservative solution, and we've seen that these are generically unstable under small perturbation. These are linear instability. So within GR, this form of singularity, without the field equation, we cannot prove what is going on. And then we have explored some possibilities. And we have also seen that observation of these objects are quite difficult to study, but nonetheless, with all the data that we have, this is exciting time. So we should keep studying the phenomenology, especially. So yes, I finish here. And,
Okay, thank you very much for your very interesting talk. I see just a question from Alexei. Alexei, please ask your question. Are you here?
Yes. Thank you very much, and thanks, Francesco, for your interesting talk. I'm a bit curious. As I understand, maybe I'm wrong, but do you have an idea from which model you will get these beautiful geometries? To which, I don't know, modification of gravity, this can be a solution?
Yeah, so actually this, especially the regular black hole ones, these come up in several places. Overall, so the idea is that if you want to avoid the singularity, so you need to weaken gravity, and if you do that, often this is what you get. So you have models coming. These are, I think they are more toy models that quantum gravity studies, but toy model inspired by loop quantum gravity, inspired by asymptotic safety, you get this kind of objects. This actually, there are many things in the literature, and I just wanted to study the common characteristic of all of them. I didn't want to marry a specific one. This is something that is quite simple to get, because you take a spherically symmetric metric, and then you change the mass function to avoid the singularity. This can come out from many modifications. Just switch off gravity at very high energy, you will get something that is similar to this.
I cannot say that
limited.
I cannot say I agree with you that it's really easy to get. Asymptotic safety approach is cool.
No, it's.
But I mean, it's really requires you thinking about some non-local operators or whatever, which I agree to talk
it's
about.
Really easy to get in. It's really easy to get in into a models. I'm not saying that it's easy to get a consistent quantum gravity computation that gets there. What I'm saying is that if you have a toy model,
curious what can be a toy model.
It's very likely that you get this.
R-squared gravity will not give this, for example. So you have to go beyond of this.
Like if you impose a limit value for the curvature invariance, I think this is something very reasonable that you can get. If you get something like an asymptotic safety spire model, I think that I have some problem that I don't understand there. But if you just suppress the Newton constant of high energy, this is what you will get.
No. See, if I start from Lagrangian, if I start from Lagrangian, I cannot really suppress anything. Whatever equations give me, they give me. I cannot just say that they must stop evolving. But another question which I have, which I didn't get really. So you say that there is some variety of geometries where there is no singularity. Is it finally geodesically complete?
Yes. So that was the assumption, the initial assumption, right? So that we were casting.
Assumption I can imagine, but when you write this geometry, can you prove that it is complete?
Yeah. So that's okay. This is what I was going to say. So we are giving classes that are saying that are so these classes are say if you have a geometry which has these required properties, it has to go inside one of these classes. We are not providing any specific geometry. This was not our goal. And of course, actually, if you study the regular black hole geometry, these ones, in the static configuration, these are not geodesically complete. You have Cauchy horizons. But if you put some time dependence, this can be like this diagram here. This is the Peros diagram of these geometries, and these are not geodesically complete. But if you have something which is time dependent and is giving something like this is going to be geodesically complete.
So do you claim that it's impossible in your construction to have a static and geodesically complete black hole or whatever black object you name it?
Well, if these ones, yes, these are not geodesically complete. Yeah.
So so this was practically my question. So what you are saying that in order to reach geodetic completeness in your construction, which would be, I guess, a goal after you want to construct something singularity free, you are saying that you need time dependence.
Well, but you need time dependence to form this object anyway, right? So it's not like you need to put something, adding something more. This time dependent is something
to form it, there,
yes. Right? Even Schwarzschild, there is no,
to form this object, yes, but like, then I observe it in the sky, it stays for some extended time. Well, maybe the proper time inside of a black hole, it's not too much, but still.
Yeah, but even from the exterior, this could be an extremely long time anyway. It's fine, but you need time dependence for sure.
I see.
This is
okay. Thank you very much.
Okay, we have a next question from Norma Sanchez. Please, Norma, ask your question.
Hello, thank you. Can you hear me?
Yes.
Yes.
Thank you.
I also see, just a second. I seen the slides. They wanted the references, so I just leave these are some references. So
okay, thank you.
So I leave them here. So like you interested, you can check. Okay, please go with the question.
Thank you. I find rather confusing the formulation of the problem and the solution of the problem itself. I mean, you can, of course, find, placing yourself in classical gravity, whatever general relativity or some classical extensions, which I do not recommend because general relativity classically, say non-quantically, is an excellent theory. Anyway, you place yourself in this framework and try to find regular, what you call regular black holes. Of course, you can try to find solutions, and but that is not the right motivation for the singularity-free problem. I mean, first, perhaps your solution here have incompleteness or inconsistencies, I mean, instabilities and so on, and perhaps the name black holes is too much, I mean, is abuse of language here. But I mean, in my mind, the problem, I mean, the right way to formulate the problem of singularity is within a framework of quantum theory, including quantum theory. I mean, quantum extension of the quantum theory to, I mean, to the energies and lengths in which the quantum effect of gravity are important, as is the case. I mean, everybody knows that it is the case for the strong, I mean, and high curvature regions in around singularities. And I finish with this. And by the way, it is also well known that the excellent theory of general relativity and the excellent theorems by Roger Penrose and Stephen Hawking, and then other extensions cannot predict the singularity in the final theory, which is quantum gravity. I mean, because it's just extrapolating. The singularity appears in general relativity mathematically, and that is perfectly correct, but not physically, because physically the theory cannot be extrapolated beyond quantum length or quantum energies or quantum curvature, Planck length, Planck energies, or Planck curvature, and so classically. And so this is the framework, I mean, on the items which should be at least, I mean, very trivially, start to be posed to address the problem of singularity. Now, if you just want to play, or I mean, to address the problem, of course, of investigating all these possibilities of solutions, that is perfectly correct. I mean, and many others. I mean, I think many colleagues have addressed the problem of regular solutions, black hole. They need to introduce another kind of matter, perhaps at the center. There are different, even for wormholes. Thank you.
Yeah, so, okay, you said so many things. Let's see if I remember all of them. So overall, I would say, of course, I mean, most of the things you said are things that I also said in the introduction. So
no, but you don't say in this way. I mean, you address. And you address always. No, because you address always in terms of toy models. I mean, you address quantum theory marginally, and you go to toy models.
Yes. So, of course, if I was saying this way, I would not have worked on this problem, but because I understand your point of view, and it's definitely a legitimate point of view. The point is, what I'm trying to do is something which is as model independent as possible. So, of course, the right way to solve this problem, if I knew which one was the quantum gravity theory, is take the theory and study the theory and look at the consequences of the theory, and then maybe look at the effective description that this theory have, and see if some of the effective description can be in one of these classes. But of course, we do not know what is the theory of quantum gravity. So we need this approach, but we also need some other approaches. So I'm not saying that this approach that we are doing is completely, is per se is enough. I'm saying that there are limitations, and I think I was stressing what are the limitations in my opinion. On the other hand, I also think that there are some strengths. The strength is that this is completely generic. Every time that you have an effective description, it will go in one of these classes. So there are hundreds of papers in the literature that are described in one paper that we have put out. And okay, you don't like it, it's completely fine. You don't like, we need to work on the same topic. The fact that GR does not predict the singularity, of course. I mean, I said that the singularity is a point missing from the manifold, cannot be described by general relativity. We should not say that we have no idea what's going on with the singularity within general relativity. The theory breaks down. Now, the question is, can you have an effective description? Maybe yes, maybe not. If not, we need to study all the possible UV completion of the theory. And this is something that we have to do. And it's not what I am doing. I mean, there are many people doing that. What I'm doing is that if there is an effective description, instead of going case by case, which will be a lot, I'm trying to have some description which unify all of them in a way. And of course, the result is not going to be as bulletproof as if you take one model and you do the computation within that model. But I mean, I think I've stressed in many universal results that are quite interesting. And of course, I mean, I mentioned many times, if the first assumption I'm making is going to break down, at least the geometric classification part is going to be to fall. I mean, we will not be able to trust it anymore, and it's completely fine. I mean, this is physics. We have many possible directions, and at the end of the day, if we find something which phenomenologically can be tested, we are trying to test it, and then the experiment will tell us if it is fine or not. I don't know why a priori we should exclude this possibility, but I mean, it's okay.
For the problem, I finish now. I mean, I don't. I leave the time to the other colleagues who are waiting for discussion. I think that this. I mean, you can play finding solutions of general relativity or extensions on the way you pose the problem classically, and you can continue, but you don't go too far in addressing the problem of what are the issues of the singularities in a theory like a general relativity, that is the important problem. I mean, how to extend and how to avoid in a right way the singularities, the mathematical singularities of general relativity. So the direction is quantum theory, and the direction is going beyond quantum theory we have at hand. That is, we need to reach Planck scales and beyond Planck scale and do and try to do progress. I mean, this keeps you with the classical finding classical solutions. I mean, and you can say in defense that is because of trying to do generality, but generality in avenues or in line of research which do not give you the answers, on which are not essential for the answer. I mean, you can do generalities and more generalities, but you don't solve the problem or don't face the right problem. So I think that the avenue of quantum theory addressing the problem of interior of black holes and singularities and cannot be avoided, and a knowledge of that is necessary to take it into account to make progress. of course, you can continue, and there are a list of reference and so on. Saying that in a positive way to really make a progress in the problems you are addressing.
Yeah, I mean, I don't understand why you are so extreme, but of course, I mean, I'm not claiming that I'm solving the singularity. I'm just saying if there is some effective description.
I'm sorry, I am not extreme. I just it's nothing personal. It's just trying to pose a problem. This is a seminar of quantum gravity, of quantum and all that, and so. We know the importance of addressing the problem of singularities and the problem as hard it is, and how we need to make progresses. And so it's our duty.
Yeah, I mean, I don't know how strongly we can say we know how to make progress. We need to explore different directions. I think, like, I mean, if we know already what was the right direction, of course, we should all do that.
Yes, quantum theory. Quantum. I already said enough about the right direction, which is not the final and the complete, but we need to go in the quantum direction. I say that and explain why, and I think I think is what I am pointed out.
Yeah, but I'm not discussing with you about the importance of the.
If I can make a comment, maybe if I can just make a comment, maybe to make peace here.
Just a second, Luca. Just want to say that I mean, we have to explore several directions, and I don't understand why you're saying you should not explore the possibility of having an effective description. And I understand that this is likely to break down. I mean, I didn't do any extremely strong claim saying this is the full description or anything like that. I'm saying that there are some limitations and there are some strengths to this approach. I was stressing the limitation. I also think that there are some strengths, and if you disagree, it's fine. I mean, we don't need to work on the same topic, so it's okay. Luca, what do you want to say?
Yeah. So what I want to say maybe is that from a physical point of view, so what Francesco maybe is doing is that even if there is a quantum theory of gravity, which quantum mechanics, let's say, will solve this singularity problem and so on, maybe what Francesco is saying, there will be some semi-classical regime where some effective geometrical description hold, and then this consideration can apply, right, Francesco? Maybe that's what maybe.
Yes, and of course, this is by no means obvious. I'm not saying that.
Sure.
I'm never saying that.
It's an assumption.
It's a working assumption in order to use some tools that we know well, that we can we know how to use them to study a problem, then to find some consequences, and hopefully to test them at the end of the day. And if you do not like the results, okay, we go back and we say, okay, this assumption was not working. But I mean, we need to study these problems. Like, I'm not saying that this is the right solution. I'm saying that we need, I mean, the community is made of different people, and we should study different approaches. If we all go for the same one, what if that's not the correct one, right? I mean, I'm not understanding. In a way, it's that I'm not saying that this is going to be realized. I'm saying that this is something we need to study and see if nature is, if it's going to give us some information. And I think we can extract some information from here. Even if the assumption breaks down, we can extract some information anyway.
Okay, maybe we can go, thank you for this discussion. Maybe we can go to the next question. We have a question from Valery Frolov. Valery, please ask your question.
Okay, thank you. Suppose a black hole interior is regular. So you asked the question at the beginning, it's a natural question, can we observe this? So you mentioned two options. First is that final state of evaporation where it should be important. I totally agree with this. At the end of your talk, you mentioned other option to have some information about the regular interior from the observation of the large black holes. So, but I don't understand this. So suppose we prove that there is a deflection from Schwarzschild or Kerr geometry at the radius of, I don't know, 1,000 kilometers and so on. You don't have theory. You don't know how to continue to the interior. I easily can construct continuations which are both regular and have singularity. So what is information can you have from the requirement that its interior is regularly continued? There is any possibility to do this, or it's what is your guess?
No, okay. Yeah, for the phenomenology part, I was a bit fast. So we identified these classes, right? And of course, for regular black holes, you can have. I mean, the point is that the geometry from the exterior, like if you have some specific model regular black holes, you can test it. But the point, as you said, you can change the geometry in the interior without changing it outside, right? And this will make it impossible to test. So yeah, for regular black holes, I was studying the geometry, I was studying the issue of mass inflation. And then there are some channels to cast constraints. There are people that are studying quasi-normal modes, that are studying these kind of things. But of course, the constraints that you can cast are very, very geometry dependent. Like you take Bardi and Hayward, you cast the constraint, but they are very weak, right? If you study the shadow of regular black holes.
So just a minute. Yeah. A question is that not because it's weak, small, let's consider future and it will be more exact. So my question is that you find something at the near horizon exterior. You don't have solutions which you test. And there is ambiguity. So it's easy to construct regular black holes with a polynomial, and it's infinite number of continuation which are regular. And it's infinite number of continuation which are singular. So you cannot distinguish them and say that my assumption is correct. So I can understand at least why. How you can.
No, I completely agree. Yes. So the phenomenology I was focusing mostly on this last class, and I was the way you do it is I mean that test that was there. You make some. You make some there were some assumptions made on the properties of this class, like you reach thermal equilibrium. That we challenge this assumption. We show that you might not reach thermal equilibrium if you have absorption. But of course, this is a very, very, very tricky program, and of course, phenomenologically, it's going to be very, very difficult, and of course, once you test the geometry outside, not even at the horizon, you test it farther away from the horizon, and you can continue in different ways. Yes, this is a definite limitation.
If there is no horizon and you technically don't have black holes, it has either a regular or singular interior. So again, it's not the distinction between regular and irregular. So you modified your model, but regularity of the interior can be tested for microscopic black holes. It looks like visible, but for macroscopic, it's not so easy.
But unfortunately, the data, the experiments are for macroscopic, right? So this is why I would say, like, we need both theoretical studies of the geometries. Maybe try to argue that one geometry could be theoretically disfavored for some reason, like the stability, and then hope that the endpoint would be something which give you some modification outside that are the ones that you're going to be able to test it. But of course, then the test will be model dependent, like because as you said, the geometry can be continued in different ways. Of course, yes. It's a tricky problem. Thank you.
Okay. I saw that there was a question from Hong Wu. Do you still want to ask question? Are you here? Huang Wu.
Okay.
If you wish to ask a question, please do this just now.
I I asked one question. I don't understand the back reaction. What kind of back reaction? What kind?
Okay, so the back reaction you said, right?
Okay. Huge
Yeah.
variation
So-
from the geometry. Yeah. What kind of this?
So,
Hmm.
this is, so let me stress again what is that can be done in a completely generic way, and what will depend on the specific model and the specific field equation of the model. Completely generic, you can say that once that to this background geometry you add this type of perturbation, you can make some minor assumption, the ones I was explaining before, and you can relate the geometry in the for this specific perturbation. You can relate the geometry in the 4 region of space-time that you create, and this allow you to say that the Misner-Schott mass and hence the curvature invariance in the region between the 2 shells grow and grow and grow, and so they keep growing the closer you get from to the inner horizon. And this is what I mean by huge back reaction. That if you trust the model, it's actually going to be infinity. However, what I say is that the model at some point will break down, and you will not be able to. You should not trust it anymore. So at some point, you will need to pick the some field equation that give you this geometry as a solution, and see what is the back reaction. So this is yeah. So basically, this result is telling you that the different toy models that give you these space times, these are in a sense incomplete analysis, because as soon as you put some small perturbation, you will get something large back, and it will be interesting to study then the nonlinear problem, which is of course much more difficult than study the geometrical way, which is just a partial answer. I hope this answered the question.
Okay. More questions, please, or comments or remarks? If not, thanks once again our speaker. Thank you very much, Francesco, for your very interesting talk. And I also would like to thanks Norma and Valerie for very essential comments and remarks. Thank you very much. Yes, thank you.
Thank you, Francesco.
Thank you.
Bye.
Thank you.
Bye-bye.
Thank you, Rina, and all of you. Thanks.
Yeah.
Thank you.
Bye-bye.
Bye-bye. Bye-bye.